You might have noticed the pigeonhole principle I've been using most of the time is this one, the one about injections. So more pigeons than holes means some pigeons will be in the same hole. Sometimes I've used this one. Every once in a while I've used the smooth injections one, but I have almost never used this one. And now I'm going to change this. I would say the surjections one is indeed used not less often than the injections one, but it's still an important fact. So let me come back to endofunctions. First, a notation: if f from x to y is any map between two sets, and if u is a subset of x, then f of u is defined to be the set of all images of elements of u under f. This is a subset of y, and is called the image of u under f. So let's study the image specifically for endofunctions. So given an endofunction f of a set x, we can consider the images fi of x for all I in n, because we can apply f multiple times. That's what you get from having an endofunction. For example, if f is given by the following diagram, again, this is a 12-element set, and the arrows show what elements are sent to what elements. So you see a cycle here, and everything else at some point converges into the cycle. What are the images? So first of all, f to the 0, if you apply the f 0 times, you're just applying nothing. So it's the identity map. And that's the image of the identity map is the whole set X. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, what happens when you apply f once? So 11 is not in the image because 11 is not hit by a single arrow. So you lose 11. You also lose 7 and you lose 10. And you lose 3 because 3 is also not hit by anything. So what remains? The cycle remains, and also 8 remains and 0 remains. 8 is the image of 11 and 0 is the image of 3. What if you apply f again? So what if you apply f twice? 8 disappears now because 8 is the image of 11, but 11 is not the image of anything. So 8 is not the image of anything under f square. The cycle is still there, and basically that's it. Only the cycle remains. And if you apply f again, you will see that it's still the same thing, only the cycle remains. So fn of x equals this for each n at least 2. So the pattern here is at the beginning the set is the whole x, but then it starts getting smaller until at some point it has only the numbers that belong to the cycles, and at that point it just stays unchanged from there on. So this pattern generalizes. I will state it as a theorem. Let x be a finite. Actually, it's in the notes. It's a proposition. Let x be a finite set. Let n be its size. Let f from x to x be a map or an endofunction. Then, first of all, the images become smaller in the sense that each one is a subset of the previous one. It's a decreasing chain of sets, as people call it. Secondly, if at some point it does not change, then it will never change from that point on. So if some I satisfies fi of x is fi plus 1 of x, then fi of x is fi plus 1 of x is fi plus 2 of x is fi plus 3 of x, and so on. So in other words, fi of x is of k of x for each k being at least I. Third, it does. So the third claim is that it does stop changing at some point, and not later than at the point n. So fn of x is fn plus 1 of x, is fn plus 2 of x, and so on. This doesn't mean that it has to change all the time before fn. For example, here it stops changing at f2, whereas n is much bigger here. By the way, this n is not this m. Let me call it m. And finally, if you look at the set f to the n of x, there is a certain map defined on this set. The map fn of x to fn of x that sends each x to f of x is well defined and is a permutation of fn of x. So intuitively, this is pretty clear. Fn of x is only those elements that are in the cycles. Here we have only one cycle, but if you go back to that example, we have 3 cycles. And Fn of x just contains the element in the cycles and none of those other elements. So if you restrict yourself to the numbers, to the elements in the cycles, you notice that at that point you just have the cycles left. So if you follow the arrows, you will always come back. And this is why you get a permutation. But formally speaking, what I think is the easiest way to do it uses the pigeonhole principle. So let's do part A first. This is pretty easy. We must show that fi of x contains fi plus 1 of x for each I in n. Indeed, if p is an element of fi plus 1 of x, then p is fi plus 1 of x for some little x, so that p is fi plus 1 of x. Now fi plus 1 is the same as fi after f of x. So it's fi of f of x, but f of x is an x, so this is in fi of x. Therefore, fi plus 1 of x is a subset of fi of x. So basically, this is saying if p is an image under fi plus 1, then it's also an image under fi, because fi plus 1, as they say, factors through fi. So you can just cut off the last f, basically. And this means the same as fi of x contains fi plus 1 of x. So part A is done. Now part B, this is an induction. So let I in n satisfy fi of x equals fi plus 1 of x. I'll just show the main idea. You can fill in the rest. I want to show that fi plus 1 of x is fi plus 2 of x. How do I connect them? I write fi plus 1 of x as f after fi of x. So this is f of fi of x. All these equality signs, you can easily check them. This is, of course, we're not applying a map to a single element here. We're applying it to a whole set of elements. But nevertheless, all these things are true. So if you apply a composition to a subset, it's the same as first applying the inner map and then applying the outer map. fi of x is the same as fi plus 1 of x by assumption. So this is f of fi plus 1 of x. This is the composition again. And this is the same as fi plus 2 of x. So we started with fi of x being fi plus 1 of x, and we concluded that fi plus 1 of x is fi plus 2 of x. The same reasoning now yields fi plus 2 of x is fi plus 3 of x. Basically, we are raising both exponents on both sides. And we can keep doing this over and over. Fi plus 3 of x is fi plus 4 of x, and so on. This doesn't mean that any single element will be sent to the same place as under fi and fi plus 1. It only means that if you look at the set of all images of fi and the set of all images of fi plus 1, so all values, the sets will be the same. And combining these equalities yields exactly this chain of equalities that we want. So part B is solved. Now part C. So part B says that if this chain stops changing at some point, or if there is one of these signs that's actually an equality sign, then all the signs afterwards are also equality signs. Now we actually need to prove that this is the case. So let's look at these numbers again. So not numbers, for sets. Part A yields that we have this chain. Therefore, we have this chain of inequalities between the sizes, because a subset always has at most as many elements as the surrounding set. So if this is if this set contains this one, then its size is at least as big as the size of this one, and so on. However, and I'm gonna stop this chain at fn of x, or actually fn plus 1 of x. That's the best place to stop it. And that is, of course, at least 0. Whereas this is at most n. I mean, actually, it is literally n, because f0 of x is the whole set x, and that has n elements. So you have a decreasing sequence of numbers between n and 0. And how many numbers do you have? You have n plus 1. No, you have n plus 2 numbers, integers, actually. So these integers are n plus 2 integers between 0 and n inclusive. But there is only n plus 1 integers between 0 and n. So we have again too many pigeons and too few holes. So by the pigeonhole principle, 2 of these integers must be equal. And because they're weakly decreasing, because they're in decreasing order, this means that the consecutive ones are integers, are equal. So there is an I for some I between 0 and n, such that these two consecutive integers are equal. Consecutive, I mean in this chain, not consecutive as integers. Because if this wasn't the case, then all of these greater equal signs would be greater signs, and greater signs would make all of the integers distinct, but they cannot all be distinct by the pigeonhole principle. So I must have an equality somewhere in this chain. Okay, consider this I. Now, fi of x is fi plus 1 of x, so that part B yields that For now, it's not the sets being equal, it's the sizes being equal. However, part A, this chain here, it shows that fi of x contains fi plus 1 of x as a subset. Therefore, fi plus x is a subset of fix that has the same size as fix. Now, if you have a finite set, which subsets of it have the same size as the set itself? Only one subset, namely the whole set. Therefore, fi plus 1 of x must be fi of x, because the only subset of a finite set U that has the same size as U is U itself. All the proper subsets have smaller sizes. So fi of x is fi plus 1 of x, and this time we have an equality of sets, not just of sizes. And therefore, part B yields that part B says once you have an equality between two consecutive sets, all the following sets are also equal to them. So all the sets starting with fi of x will be equal. And therefore, all the sets starting with fn of x will be equal, because n is at least I. So all of those subsets will be somewhere in this chain So maybe n is I plus 3, and then they start here, for example. So this proves part C. And finally, part D. Let me just copy this proposition so that it doesn't disappear above the on the previous page. So why is this map well defined? That's the easy part. Well, so we need to check that f of x is fn of x for each x in fn of x. But this is clear. If x is in fn of x, then f of x is in f of fn of x, which is fn plus 1 of x. Once again, this is pretty clear for single elements, but it's also true for sets. And fn plus 1 of x is a subset of fn of x by part A, for example. Okay, so the map is well defined. If you have an x here, f of x will be here, so it really goes from the domain into the target. Now, why is it a permutation of fn of x? And this is the part where we're going to use the pigeonhole principle for surjections. We shall show that it is surjective. Once this is shown, we will use the pigeonhole principle to conclude that it is bijective and thus a permutation. So let's prove surjectivity. Let me call this map G. So G is a map from fn of x to fn of x, and G of x is f of x for each x in fn of x. Why is this surjective? Well, let's pick any y in fn of x, or let me follow the notes and call it z. Then z is in fn of x, which also happens to be fn plus 1 of x because of part C. That's where we use this decreasing chain of sets does not stops changing after n. So by part C. Hence, z equals fn plus 1 of w for some w in x. And thus, z if fn is fn plus 1 of w is f of fn of w, but fn of w is of course in fn of x. So again, let me say it this way. Fn of w is an element of fn of x. So I can apply g to it. G is defined on fn of x. And if I do this, I get exactly the same as when I apply f to it. So I get this equation. And this shows that z is an image under g. So z is a value of g. Thus, we have shown that every element of fn of x is a value of g. So the map G takes every possible element of the target set as a value. In other words, G is surjective. And now, the pigeonhole principle for surjections shows that if a map between two finite sets of the same size is surjective, then it is bijective. So, part C of the pigeonhole principle for surjections shows that G is bijective, since G is a map from fn of x to fn of x, and fn of x is a finite set, and of course it has the same size as itself. In other words, G is a permutation of fn of x, which is what we wanted to prove.